Hi, I'm Brian Mullin, and this is Balls Out Physics, Episode 6, Perspective. This is one of the biggest arguments in the flat Earth versus spherical Earth debate, and it really is all about how we see, or how we perceive our world, the world around us. As I got into this debate over a year ago, a lot of people would say things like, "Why can't I see Mount Everest from California? Without an Earth's curve, I should be able to do that. Why can't I see the Statue of Liberty from the United Kingdom?" Things like that. And people would say there's a curve blocking our view, that's why we can't see those things. But that's not really the case, because we can't see things infinitely far away. And to show an example of this, just take this eraser. This eraser is about 1.5 inches by 3.5 inches. And as I move it away from the camera, you'll see that it gets smaller and smaller and smaller. And eventually it would get so small that it would just disappear from your view. You wouldn't need a curve or something to block it from your view to not be able to see it anymore. And that's how perspective somewhat works when it comes to objects. In the scientific world, engineering world, we don't really talk about how our vision works very much. At least I never did. And I never really thought about it until I got into this debate. And we're born into this world, and we start looking around, start seeing things. It becomes pretty obvious to us how our vision works. It's kind of self-explanatory, really. And we never need a tutorial. It's just, something's close to your eyes. You know it's close, far away. You flinch when things get close to you that look like they could hurt you. It's pretty obvious. But artists, on the other hand, they do talk about perspective, because when drawing three-dimensional scenes in 2 dimensions, perspective is a big deal. And so my fiance let me borrow this children's art book, and here in lesson 77 they've got this shown here in figure B. Here they're trying to illustrate how to draw this old western town. It's shown up all right. How to make the buildings look like they run alongside a road off into the distance out here to the vanishing point. Okay. You can see the horizon's out here, all flat, of course, but that's just how it's drawn. And so perspective has a lot to do with how we perceive this world. And one of the best ways to start visualizing that is to think of looking down a long hallway, or look at a picture of a long hallway, or looking down a long hallway. You'll notice right away that the floor and the ceiling appear to be sloping toward each other, or the floor appears to be sloping up, the ceiling appears to be sloping down, and the walls appear to be sloping toward each other. Now we know the walls are plumb, and the ceiling and the floor are level, or they should be, and yet they all appear to slope towards the center point at the end of the hallway, however long the hallway is. And the corners also appear to follow this apparent slope towards the end of the hallway, but they don't. And something else to think about is that if you look down a long hallway and you crouch and then stand up, and crouch and then stand up, you'll start to notice that the floor in the hallway, the apparent slope of the floor in the hallway, decreases as you crouch and increases as you stand up. And the opposite is true for the ceiling. The apparent slope of the ceiling downward tends to increase as you crouch and decrease as you stand up. The floor appears to slope up, the ceiling appears to slope down. I think that's very important when it comes to the flat Earth debate, because this is how the ocean looks over as it approaches the horizon. When you stand on the beach, for example, and look at the ocean, look out over the ocean, you see the ocean appear to slope up towards the horizon. Another thing to notice on the beach is if there's clouds out and you see birds flying around, if you really think about it, in your view, birds that are close to you actually appear to be above clouds. But just because you know how your vision and perspective works, that the birds are actually closer to the earth than the clouds are, but you still tend to see that. Very interesting to talk about how our vision works. It's pretty remarkable, and I think we take it for granted. And so Another thing that's argued in I guess this falls into perspective, is a lot of people say we know the Earth is a globe because when you go up in elevation, you can see farther, and people claim that that's because we're able to see over the curve. But I think that while that may be true on the globe model, it's also true on a flat Earth model. And that's because of that apparent increase in slope of the floor or the Earth. So assuming the Earth is flat, if you take this level, okay, and I hold this level to you, and try to keep it as level as I can, and look at the bubble, and I move it down, you can see more of the level as it moves down and up. You can see more of the ruler marks on it, and less as it goes up and down. And so on a flat Earth, you'd still be able to see more by going up in the air. So it's not a valid argument to say that the Earth is a globe because of this. I think on both models you'd be able to see farther as you go up in elevation. I think this is a pretty good proof of it. So a few days ago, I was sent a message by someone who has been questioning the heliocentric globe model, and he's what I like to call a closet flat Earth researcher. He's got a technical background, and he basically sent me a message because he's got nobody else to talk to about this because it's taboo to question our world. But he sent me a video. He said he's really doubting the globe model, but the video he sent me was by a YouTube researcher named Red Pill World. And Red Pill World has been using a theodolite, a surveying instrument, to measure angles over long distances and compare that to the angles you would expect to get on a spherical Earth versus a flat Earth. And in one of his videos, he did an experiment between Warren Dunes Park in Michigan and Chicago, basically using the theodolite to measure angles across Lake Michigan, angles from the horizon, from level view to the top of the Sears Tower, or a couple points on the Sears Tower, and the base of the Sears Tower. This is a really good video to analyze in this perspective video, because I think Red Pill World did a really good job. He said he's not a surveyor, but his calculations were pretty good. I spent a whole day going through all the calcs and just thinking about what he had done, and he concluded that the Earth is a sphere, but I don't think he accounted for the sloping effect that you would have on a flat Earth due to perspective. And a theodolite does work off of sight. You have to look through the crosshairs in the theodolite to use it. It's also another instrument used in surveying is called a sight level. It works the same way. It's kind of like the scope on a gun or anything that you look through that has a crosshair. The user, the person's vision has to be used for the device to work. And we all are subject to this law of perspective, this way we see, so it can affect what we're doing. And now typically, survey sight levels are accurate up to about 150 meters. I did a little research on it. I posted an article about this in the link below, and or in the description below. And so 150 meters is about 500 feet. And theodolites, I think that the maximum range I saw was about 1,000 meters, which is a kilometer, and that's less than a mile. And the distance from Warren Dunes Park to Chicago is about 53 miles. However, I still think the experiment's good. I don't think we should just throw it out because these devices aren't supposed to be used at those great of distances. For real professional surveying applications, of course, they can't use it. I mean, no surveyor would use it for this. But this is just an experiment to see what happened. And so you might want to watch this video. I posted the link in the description. Before going any further with this, I'm going to go over some of the basics in this. I may put some clips here and there, but so you may want to pause and then go from there. Alright, so assuming you watched the video. In the video, Red Pill World did calculations for both a flat and spherical Earth. And so if we if we assume without the effects of the sloping effects of perspective on a flat surface of the Earth, of the upward sloping effect, this expected drawing up here is what you would think you would see. So if we have the theodolite over here at 778 feet above mean sea level, and the Sears Tower over here 52.3 miles away, and the top of the tower is at roughly 2,050 feet above mean sea level, then you should be able to just use a simple right triangle to determine what angle you should measure with the theodolite to the top of the tower. The angle you should have, the angle the theodolite should calculate from having to rotate the device up from perfectly level view, assuming that this, perfectly level view from the theodolite right here, what angle would be measured by the theodolite here, as shown. So this is simple trigonometry, okay? You've got 52.3 miles, which is 276,189 feet. That's your adjacent leg for your right triangle. And then your opposite leg, okay, this would be the hypotenuse, the sight line. The opposite leg is 2,050 feet minus 778 feet gives you your opposite. So your opposite leg, the inverse tangent of your opposite leg divided by your adjacent leg gives you this angle, which is 0 degrees, 15 minutes, and 47 seconds. Okay? And surveying, angles are typically given in terms of an hour, and for precision, that's what the devices give. If you want to convert that into a decimal angle, something that you can you may be more familiar with if you've never done any surveying or worked with this, you can just say 0 plus 15 divided by 60 plus 47 divided by 3600. That gives you 0.263 degrees. Very small angle, okay? Very small angle up. That's what you should expect to see. But that doesn't account for all of the sloping effects due to our perspective, due to the user's, Red Pill World's perspective, due to his eye. And so this is what you would think about if we were looking at this. If we could see the Sears Tower and the theodolite, we would expect to see this. If we were at a distance, if we were perfectly perpendicular to his sight line, or to this distance that was calculated with GPS coordinates, if you watch the video, we would expect to see this. But we would also have our own perspective effects going on here. We would actually see the lake sloping up. But this is just an idea of how to visualize this calculation, how it was done. I've got the actual down here, but I'll talk about that in a minute. And to give you an idea how the theodolite works, just to give a quick rundown on what he was doing in the video in case it doesn't make sense, is I drew this unit circle here with 90 degrees being straight up. I put 180 degrees. Typically a unit circle goes counterclockwise, but I just drew it this way because of how the sketch is drawn. So 180 degrees over here, 0 degrees here. Imagine this eraser is the theodolite, the device that's on the tripod that he was using in the video. Okay? When it's perfectly leveled out, when the scope is pointing perfectly level, straight out at the horizon, I mean the scope, the crosshair is level, okay? Does that make sense? Then the angle on the theodolite will be 90 degrees because it's working off of a vertical angle, not a horizontal angle, okay? So if he has to rotate it up to get what is expected here to get this angle, then he would get 89, or he would get 90 minus this small angle would give 89, 89, I can't figure that out in my head in minutes and seconds, but you see what I'm saying. You would subtract this angle from 90 degrees, and you would get 89, I'll do it in my head, 89 degrees, 45 minutes, and 13 seconds is what you would get, right? I hope my math was right there, my head math. So, if you watch the video, that's not what he ended up getting, but we'll go over that. He also did calculations for spherical, but I'm arguing for flat Earth since he argued for spherical Earth on this experiment. So if you watch the video, I've set this board up here based on what you saw at about 5 minutes and 30 seconds. He showed a shot through the theodolite of the crosshair right down here at the base of the building. This is looking across Lake Michigan, okay, from Warren Dunes Park at an elevation of 778 feet. Okay, he shot down here to determine the distance to the horizon, and he got an angle of 90 degrees, 13 minutes and 40 seconds. And he calculated where the horizon would need, where the horizon, the angle to the horizon that you should expect from horizontal view or from 90 degrees vertical angle, perfect vertical angle with the theodolite leveled. He calculated what that angle should be, and it was around 14 minutes, a little over 14 minutes. I think this is about a minute off. I don't remember the exact number. And so he concluded, mainly because of this number, I think, that the Earth is spherical. Now, he also calculated what angle should be expected to the top of the tower, which was, using a vertical angle, the distance below level view. He calculated that would be 90 degrees, 6 minutes and 47 seconds. He actually subtracted this from 0, and it was a negative 6 minutes and 56 seconds. But I'm going to use it in terms of what the theodolite measures. So it should have been 90 degrees, 6 minutes and 56 seconds for a spherical Earth. That's where the top of the tower should have appeared. Okay? So, arguing for a flat Earth here, first of all, he also calculated what the expected angle should be, vertical angle measurement should be to the flat Earth horizon. He assumed that the flat Earth horizon should be at the base of the building. Okay, and he got an angle of minus 2 minutes and 24 seconds, I think, which would be 90 degrees, 2 minutes and 24 seconds measured by the theodolite. But there's no need to calculate the flat Earth horizon. The flat Earth, the true flat Earth horizon would always be at level view, would always be at the center of your view. Because think about the hallway, okay? The floor and the ceiling would be sloping together, right? And so on a flat Earth, the floor, the Earth, would be sloping towards the horizon, and the flat Earth and the sky would meet at this line at 90 degrees. There's no need to calculate it. So the true horizon at 778 feet would be just above the top of the tower, because he measured a very small angle to the antenna, negative 7 degrees, or 7 seconds, which that's tough to say. I mean, these are really far distances. I mean, to even bump that theodolite, I imagine would give you some type of very small measurement or angle measurement. Okay. So, assuming a flat Earth, okay, I drew here, kind of based on that beach scene you saw earlier, what a perspective should look like outside, keeping the hallway in mind. If you're outside, this is what I would expect to see on the beach or on a lake in the flat Earth model. See, the Earth is sloping up towards the horizon, and the sky is sloping down towards the horizon as well. Whether the sky is flat or a dome, I'm not going to get into that, because we're more worried about the slope here of the Earth. If the Earth is flat, it's going to slope to the horizon and meet the sky there, regardless of what the sky is doing. But we assume that the sky is sloping at a greater rate, and that's why I drew these imaginary corner lines like this, because we're so close to the Earth. We know we're a lot closer to the Earth than we are to the sky. And so the slope of the Earth is going to be a lot less. The slope of the Earth towards the horizon, the slope up towards the Earth, the rate of slope towards the horizon is going to be a lot less than the rate of slope of the sky towards the horizon. That makes sense. Okay? Think about the video I showed of crouching and standing up, and how that affects the apparent slope of a flat surface, a level surface. Okay? So, assuming that's what's going on here, the lake is sloping up towards the horizon, as it appears in Red Pill's video. If you look through the theodolite, it definitely appears. You see water looking like it's sloping up towards the horizon. Okay? And so you see this horizon here, okay? But the true flat Earth horizon should be farther away. It's up on this drawing, but it should be farther away, back in the distance, farther away than this building is, okay, than the Sears Tower is. So this right here is what I'm calling the apparent horizon. And the reason for that is seeing the true flat Earth horizon is going to be very difficult because there's air in the way, there's smog. Okay? If you've ever lived by a body of water, then you're probably very familiar with this horizon moving. On a cloudy or a foggy day, the horizon is a lot closer to you when you're standing on the bank. And on the more clear day, it moves farther away. The horizon moves based on the clarity. Okay? So this, I think, is just the apparent horizon based on that day. It was a pretty clear day, but you can see some haze in the distance, especially when you're looking through this theodolite at 5 minutes and 30 seconds. There is a haze there. You can clearly see it. And remember, we're looking at Chicago, one of the biggest cities in the United States, a very busy city with lots of cars, lots of buses, lots of vehicles creating smog. Okay? Seeing this true flat Earth horizon through Chicago is going to be very difficult. You're going to need magnification for one, and it still may not even be possible. So this horizon right here, I think, is just apparent, and if you look at it really closely, you can tell that it's not perfectly straight. It's a little jagged, and it looks distorted when you really take a look at it. You look at it in the video. And that's why I drew it kind of wavy like this, because I think it's just a distorted line we're seeing. Okay? So imagine that floor sloping up in the hallway, and that this lake and the earth is doing the same thing. If we get that apparent slope up when we look at a level surface, like we definitely do, then would we get the building kind of sloping towards us? And would that be the reason that we don't see the base of it? Because it's kind of bunched up. Think about looking down that hallway, and as you get lower and lower to the ground, the end of the hallway starts to, because the slope is so low, everything starts to bunch up. Go do an experiment with this yourself. I mean, that video I took in a hotel hallway isn't the best, but as you get closer and closer to the floor on a long hallway, you really get a lot of bunching up effect here. Okay? And so, I think this has a very big effect on how this building, the Sears Tower, appears there. See what I'm saying? I don't think that the object, going back to this eraser, there's a linear decrease in the size of the objects when you're looking over a flat surface, when you're not centered between the floor and the ceiling. Okay? Well, I've seen a lot of perspective drawings out there that flat earthers have made, or flat earth researchers, like myself, and I've seen people overlay the perspective lines on, say, a road that's going off into the distance, or a set of train tracks that's going off into the distance, and you notice that they're typically drawn like this. This is an old drawing I made to show perspective, to show the sky and the earth. And that you see these corner lines, okay? They're equal on the earth and the sky. This would only be the case if you're perfectly centered between the sky and the earth. Just like in the hallway. You'll notice that the corners appear equal, and the slope of the earth, or the ceiling, or the floor and the ceiling appear equal when you're about in the center of the hallway. So, that would also be the case on a flat earth. And I think that this distortion effect is due to the fact that we're so close to the floor, so close to the earth. And so, if you noticed on the first board I had up here, I drew an actual view, like a side view of what the perceived effect, line of sight from the theodolite would be for red pill world. So this is basically what he's seeing what he's seeing here from this side, if that makes sense. Okay? Just to try to visualize what's going on here. Okay. Okay. So, elevation 778 feet. The apparent size of the building is definitely smaller, and so he's shooting across the lake, level sight, and he had to rotate the theodolite down. You know, remember the angle was 90 degrees, 3 minutes and 47 seconds. Later in the video, he just subtracted that from a horizontal or level line to get negative 0 degrees, 3 minutes and 47 seconds. Okay, and so you can clearly see in the theodolite image that the lake is sloping up and the sky appears to be sloping down. These are apparent, right? We know that the lake is not sloping up, but it appears to be sloping up. And so the building wouldn't the building want to slope too? Wouldn't we get that apparent slope effect toward us or toward red pill world as he's looking through the theodolite? And so I think that is what is actually creating this angle here, and this bunching up as you get closer and closer to the true horizon, or to the vanishing point, which is really, I think, goes to infinity. You just have to keep zooming in to see it. But that bunching up effect as you get to the end of this slope over here is what's creating that illusion that the building is smaller. So it's tough to say. I mean, first of all, the surveying equipment isn't supposed to be used at these distances, but when you think about it, that the water at the beach or at the shore does appear to slope up. And another thing I want to bring up is from the beach in Warren Dunes Park to the shoreline in Chicago, there's a distance of 50 miles. Now, to bring back the infamous curvature chart, at 50 miles, you can see this on here. Let's see if it'll focus. At 50 miles, it's not focusing, but at 50 miles, the drop from one side of the lake to the other would be 1,667 feet, roughly. So, if you've researched flat Earth versus spherical Earth, the debate at all, you would know that the Earth curves roughly 8 inches per mile squared. So the first mile there'd be an 8-inch drop, second mile 32-inch drop. It really starts to take off. And when we look down a hallway, a flat level surface, we see the hallway floor slope up towards the end of the hallway. When we look at this lake, we see it slope up towards the horizon, whether that's the apparent horizon or the true flat Earth horizon, if you're assuming a flat Earth mile. Our eyes are very good at seeing planes. And so to think that we see this plane effect, this apparent sloping up of a plane, when we look at water like this, whether on the beach or on a lake, and that's what we see in a hallway with a level flat surface, I think our eyes would tell us that this is curving down. We would be able to clearly see that. Just my opinion. But I think this is what's happened here. I think this is due to perspective. Being so close to the Earth, the way the Earth slopes, the lower slope of the Earth as compared to the sky, is what is creating this effect, what is making this tower appear like this. And the reason we can see taller things is because they're sticking up off of the floor higher than everything else, even though they appear to be rotated towards us because of how our vision works or how perspective works. So those are my thoughts on this, and I think this is a very good experiment to go over. I think arguing how it would prove flat Earth or spherical Earth is good for debate. However, I think that this also shows that we cannot use line of sight or our eyes to try and prove that the Earth is flat or spherical because of perspective. I mean, perspective has an enormous effect on what we're seeing here. And so I think the only way to really do it is to measure the the curvature or the lack of curvature over a few miles with some type of mechanical line, or force the line, if you've seen my video on that. And a lot of people have been asking me to do that, and I think it really is the only way we can truly get to the bottom of this. However, consider what I said here. Think about how our vision works. Something else I wanted to point out is when you think about that hallway, when you're looking down the hallway and you're seeing all of the walls and the ceiling and the roof slope towards the end of the hallway, right? You're seeing that. But imagine if you could remove one of the walls to your left or right and have an observer perpendicular to the hallway who could see you in the hallway and the end of the hallway. That observer would see the ceiling and the floor parallel to each other, but you see them as sloping towards each other. So we know that would be the case because we know how our vision works at short distances, relatively short distances. So going back to this, our expected versus actual, if we were off in the distance so we could see Red Pill World and its theodolite and the Sears Tower, we would see, we would definitely see that the tower is bigger than him and that the top of the tower is higher up than him. And let's say, imagine we had a ruler, a magic ruler that doesn't weigh anything and is infinitely rigid so it doesn't deflect at all, and it was long enough to sit on the top of the tower and right on top of his theodolite. We would see it angling down just like this expected sightline, wouldn't we? But Red Pill World, would see it like this. He would see it sloping down. Kind of crazy to think about, just like the hallway. Because this would be his view. Assuming a flat Earth, then I think this is a valid depiction of what it would look like on a flat Earth with this sloping effect and how our vision works. So he would see this thing sloping up out of the tower, even though he would see it sloping up towards him, even though it's sloping down. Kind of crazy. But there's a hill in Florida, in Lake Wills, Florida, where apparently if you park your car at the base of the hill, the bottom of the hill, what appears to be the bottom of the hill, and put it in neutral and let your foot off the brake, the car appears like it's rolling uphill. And now the tourist attraction, maybe trap down there, is that there's this gravitational vortex that pulls the car up the hill. But I got my money on, if you put a level on that hill, you'll actually see that it's sloping down, and it's just an illusion due to our perspective. That's something else to keep in mind. So we need to think about how our eyes work and what we're seeing here with this world, and keep going from there. Like I said, not an absolute proof of anything, but I think it's more likely this is what's happening. That this is our true flat horizon here, and these measurements are based on that perspective effect that's occurring, if there's any accuracy at all to these measurements over 52 miles with the surveying equipment. So those are my thoughts. Make up your own mind, and love to discuss this and hopefully keep going with this and some more sub videos. So until next time, peace.